Welcome, dear friends. Tonight, we begin a quiet and hurried journey through the vast and silent expanse of our solar system, the small yet astonishing corner of the universe we call home. Floating within the darkness of space, this delicate cosmic structure was born more than 4.5 billion years ago from clouds of dust and fire. And since that time it has continued its endless, graceful motion, keeping within it the memory of the birth of stars, worlds, and time itself. Here, in the gentle balance between gravity and motion, heat and cold, light and shadow, lies a story far older than humanity, and yet deeply connected to every one of us. In this journey, we will slowly uncover how the solar system came into being, how its planets, moons, and invisible forces interact in an eternal cosmic dance, and where our small blue world fits within this immense design. We will speak of silent orbits and powerful storms, of burning suns and frozen distances, of fragile harmony sustained by laws older than life itself. And as we explore the science behind these wonders, we will also touch the quiet philosophical question that has guided human eyes toward the sky since the dawn of consciousness. What is our place in this vast universe? Tonight's story is not a race for facts, but a slow drift through knowledge and wonder. It is an invitation to loosen your thoughts, to let the rhythm of the cosmos guide your breathing, and to feel how deeply connected you are to the stars above. The solar system is not only an object of scientific study, it is a living reminder that we are part of something immeasurably larger, older, and more beautiful than our daily concerns. So allow yourself to relax. Let the noise of the world grow quiet. Imagine the slow turning of planets in the dark, the steady glow of the sun at the heart of it all, and the endless space stretching far beyond what the eye can see. Our journey through the mysteries of the solar system is about to begin. The solar system is a grand gravitational mechanism whose quiet heart is our star, the sun. Around this radiant center move 8 planets, each following its own invisible path through space, accompanied by more than 200 known moons, countless asteroids, wandering comets, and fine interplanetary dust. All of these bodies are bound together by gravity, forming a structure that is at once complex, precise, and astonishingly harmonious. The true size of the solar system is difficult even to imagine. If we take into account the distant Oort cloud, a vast spherical halo of icy bodies at the very edge of our cosmic neighborhood, its diameter may reach nearly to light years, a distance so immense that it defies ordinary human comprehension. To better grasp this scale, imagine the sun reduced to the size of a football. In that model, the Earth would be no larger than the head of a pin and would orbit at a distance of about 30 meters. The outer planets would lie hundreds of meters away, and the farthest icy frontiers would stretch for kilometers into the darkness. This delicate balance of distance and motion allows life to exist on our small world, suspended between scorching heat and endless cold. The story of the solar system began about 4.5 billion years ago, when an enormous cloud of gas and dust slowly started to collapse under the force of its own gravity. As the cloud contracted, its center grew denser and hotter, forming the early core of what would become the sun. When the pressure and temperature inside this core became great enough, thermonuclear reactions ignited, and our star began to shine. The remaining material flattened into a vast, rotating disk surrounding the newborn sun. Within this disk, particles collided, merged, and slowly assembled into larger bodies, the first building blocks of planets, moons, and countless smaller objects. Over millions of years, this quiet process of cosmic construction shaped the familiar architecture we observe today. Rocky worlds formed close to the sun, while gas and ice giants took shape in the colder regions farther away. The same process that created our planetary family also operates throughout the galaxy. giving birth to countless other star systems, many of which may host worlds still unknown to us. In studying the solar system, we are not only learning the story of our own origins, but also reading a chapter from the much larger history of the universe itself, a history written in gravity, motion, and light. The place of the solar system in the galaxy. The solar system is not only our home, but also a unique natural laboratory for studying the processes that unfold throughout other star systems in the universe. Our planetary family is located within the great spiral galaxy known as the Milky Way, a vast cosmic island that contains from 100 to 400 billion stars. Within this enormous structure, we reside in one of its quieter regions, known as the Orion Arm, at a distance of roughly 27,000 light-years from the galactic center. This position, far from the most turbulent zones of the galaxy, likely played a crucial role in creating stable conditions for the long and delicate emergence of life on Earth. Spiral arms are the great luminous structures of spiral galaxies winding regions rich in gas, dust, and star formation. They appear as glowing cosmic rivers where new stars are continually being born. Our solar system lies between the two massive spiral arms of Perseus and Centaurus, and a relatively calm corridor of space. Here, the density of stars is lower, and violent events such as supernova explosions occur less frequently. This distance from the crowded and highly energetic galactic core offers a kind of cosmic shelter, protecting our planetary system from constant catastrophic disturbances. Although our region feels tranquil, the solar system is far from motionless. Together with the rest of the Milky Way, we are moving through space at an extraordinary speed of about 800,000 kilometers per hour. Yet because the galaxy itself is unimaginably vast, a complete orbit around its center takes an immense amount of time, approximately 225 to 250 million years. Astronomers call this span a galactic year. The last time the solar system occupied roughly this same position in the galaxy, dinosaurs still walked upon the surface of the Earth. If we could step far outside the Milky Way and look back at it from a great cosmic distance, our solar system would appear as nothing more than a faint, almost invisible point among billions of stars. And yet, within this tiny and remarkable location, life emerged, a complex, conscious, and capable of gazing back into the universe that gave it birth. So far, this remains a phenomenon we have not yet confirmed anywhere else. In the vast darkness of space, on a nearly imperceptible speck of light, the universe learned to observe itself. The history of astronomy. For most of human history, people believed that the Earth stood at the very center of the universe. This ancient vision was shaped by the geocentric model developed by Ptolemy, which dominated astronomical thought for nearly 1,500 years. According to this model, the Sun, the Moon, the planets, and the distant stars all revolved around a motionless Earth. To the ancient eye, this seemed natural. The ground beneath one's feet felt solid and unmoving, while the heavens appeared to turn endlessly overhead. In this worldview, humanity occupied the central stage of creation, both physically and symbolically. A quiet but momentous shift began in the 16th century with the work of the Polish astronomer Nicolaus Copernicus. He proposed a daring new idea. The Earth was not the center of the universe at all, but merely one of several planets orbiting the Sun. This heliocentric model overturned centuries of established belief and quietly displaced humanity from the cosmic center it had long assumed. Though revolutionary, Copernicus's idea was initially met with deep skepticism and resistance, for it challenged not only scientific tradition, but also philosophical and religious conceptions of humanity's place in creation. Yet this single idea became the foundation upon which modern astronomy would be built. The next great breakthrough came at the beginning of the 17th century through the observations of Galileo Galilei. Using an improved telescope, Galileo became the first to observe the moon in close detail. He saw mountains, valleys, and craters upon its surface, a discovery that shattered the ancient belief that all heavenly bodies were perfectly smooth and unchanging. He also observed the phases of Venus, a phenomenon that could only be explained if Venus orbited the Sun rather than the Earth. These observations provided powerful visual evidence in support of the heliocentric model and forced a profound rethinking of the structure of the cosmos. By the end of the 17th century, the intellectual transformation of astronomy reached a new level with the work of Isaac Newton. Through his laws of motion and universal gravitation, Newton explained why planets move in stable orbits around the Sun. He demonstrated that the same invisible force that causes an apple to fall also governs the motions of the Moon, the planets, and even the most distant celestial bodies. Gravity, he showed, is the universal thread that binds the cosmos together. His work laid the foundation of classical mechanics and allowed astronomers to predict planetary motions with remarkable precision. From the end of the 19th century and especially throughout the 20th century, humanity entered the age of practical space exploration. Astronomy was no longer limited to distant observation through telescopes alone. It now reached beyond Earth itself. In 1969, the Apollo program carried human beings to the surface of the Moon for the first time, turning ancient dreams into physical reality. For the first time, humanity did not merely gaze at another world, it touched it. With the rise of space technology, telescopes were lifted above the distorting veil of Earth's atmosphere. In 1990, the launch of the Hubble Space Telescope opened a new era of cosmic vision. From its silent orbit above the planet, Hubble revealed galaxies billions of light-years away, stellar nurseries, exploding stars, and the deep architecture of the universe with unprecedented clarity. Each image expanded our sense of scale, age, and mystery. Thus, the path from the ancient geocentric model to our modern scientific understanding of the universe unfolded through bold ideas and careful observation, through conflict and discovery, through centuries of quiet human curiosity. With every generation, our view of the cosmos has grown wider, deeper, and more humbling. The universe that once seemed to revolve around us is now known to be vast beyond imagination, and yet we continue to explore it, driven by the same timeless question that once moved ancient stargazers to lift their eyes toward the night sky. The inner planets of Mercury. After exploring how our understanding of the cosmos was shaped through centuries of observation and discovery, let us now turn our attention to the planets that lie closest to the Sun. These worlds are known as the inner, or terrestrial, planets of Mercury, Venus, Earth, and Mars. They form a distinct family of small, dense worlds with solid, rocky surfaces, dramatically different from the vast gas giants that dwell in the outer regions of the solar system. Each of these inner planets carries its own unique story of heat, motion, and transformation. And the first among them, closest to the blazing heart of our system, is Mercury. Mercury is the nearest planet to the Sun, and everything about its existence is shaped by this extreme proximity. It orbits at an average distance of just 0.39 astronomical units, which means a little less than half the distance between the Earth and the Sun, since 1 astronomical unit equals about 150 million kilometers. Mercury's average distance from the Sun is only about 58 million kilometers. This close orbit makes it the swiftest traveler among all the planets. Mercury completes one full revolution around the Sun in just 88 Earth days, giving it the shortest year in the solar system. Yet time behaves strangely on Mercury. Although its year is brief, its rotation is remarkably slow. One full rotation on its axis takes 59 Earth days. Because of a rare and unusual orbital rotational resonance, Mercury rotates exactly 3 times for every 2 orbits around the Sun. As a result, one full solar day on Mercury from one sunrise to the next lasts about 176 Earth days. This slow rhythm of light and darkness creates some of the most extreme temperature differences found anywhere in the solar system. On the day side, Mercury's surface is scorched by relentless sunlight, with temperatures soaring to around 430 degrees Celsius, hot enough to melt lead. On the night side, in the absence of any atmosphere thick enough to retain heat, temperatures plunge to about -170 degrees Celsius. Few places in the solar system experience such dramatic fluctuations between heat and cold. Mercury lives in a constant cycle of fire and deep freeze. Though it is small, Mercury is far from simple. With a diameter of about 4,880 kilometers, it is only a little larger than Earth's moon and nearly 2.5 times smaller than Earth itself. Yet despite its modest size, Mercury is one of the densest planets in the solar system. This remarkable density is caused by its enormous metallic core, which occupies about 3/4 of the planet's diameter. The core is composed primarily of iron, and scientists believe that at least part of it remains molten even today. This giant iron heart generates a magnetic field, a surprising feature for such a small and slowly rotating world. Mercury's magnetic field is about 100 times weaker than Earth's, yet it is strong enough to create a true magnetosphere that interacts with the solar wind. Streams of charged particles from the Sun constantly flood Mercury's environment, sculpting its space near the planet in invisible arcs of magnetic force. The crust surrounding Mercury's vast core is extremely thin, only about 20 kilometers thick in many regions. Its surface is a landscape of ancient scars, densely covered with impact craters formed during the chaotic early era of the solar system, when asteroids and meteoroids bombarded young planets relentlessly. One of the most spectacular of these craters is Caloris Basin, a colossal impact structure more than 1,500 kilometers in diameter. The force of the impact that created it was so immense that it caused deformation of the planet's crust on the opposite side of Mercury, reshaping distant terrain through shock waves that rippled through the entire world. Humanity's direct exploration of Mercury began in the 1970s with the Mariner 10 mission, which flew past the planet and transmitted the first close-up images of its cratered surface. It was also Mariner 10 that first discovered Mercury's unexpected magnetic field. Decades later, a far deeper understanding came with NASA's Messenger spacecraft, which entered orbit around Mercury in the 2000s. Over several years, it mapped the planet in detail, analyzed its surface composition, measured its magnetic environment, and revealed a surprisingly complex geological history. Mercury stands today as a silent witness to the earliest chapters of planetary formation. Its surface has changed little over billions of years, preserving a geological record that reaches back to the birth of the solar system itself. In its strange motion, its colossal iron core, and its violent temperature extremes, Mercury offers scientists invaluable clues about how planets cool, how their interiors evolve, and how stars shape the fate of the worlds that orbit nearest to them. It is a small world, yet within it lies a vast archive of cosmic history written in metal, fire, and ancient stone. Venus. And next on our journey through the inner solar system, we encounter one of the most mysterious and unforgiving worlds known to science, Venus. At first glance, it seems almost like Earth's twin. It is the second planet from the Sun and Earth's closest planetary neighbor in space. In size, mass, and gravity, Venus is strikingly similar to our own world, so similar that scientists often call it Earth's sister planet. But this resemblance is only superficial. Beneath this familiar exterior lies a realm of crushing pressure, searing heat, and poisonous clouds, a true cosmic inferno. Yet hidden within this hostile world is a warning written in fire. A glimpse of what Earth itself might one day become if the delicate balance of climate were ever lost. Venus has a diameter of about 12,100 kilometers. Only 5% smaller than Earth's. Its mass is roughly 82% of Earth's mass. And its surface gravity is also very close to Earth's. If you could stand on Venus, your weight would feel almost the same as it does at home. Venus orbits the Sun at a distance of about 0.72 astronomical units, which equals roughly 108 million kilometers. Although this is closer than Earth's orbit, it alone cannot explain the planet's extreme temperatures. The true cause of Venus's hellish environment lies in its atmosphere. The atmosphere of Venus is one of the most extreme in the entire solar system. It consists of about 96% carbon dioxide, with smaller amounts of nitrogen and trace quantities of sulfur compounds. High above the surface, the planet is wrapped in thick, brilliant clouds of sulfuric acid. These clouds reflect up to 70% of incoming sunlight, making Venus one of the brightest objects in Earth's night sky. Yet the light that does penetrate the cloud layer becomes trapped below, unable to escape back into space. At the surface, the atmospheric pressure on Venus is about 92 times greater than Earth's, the equivalent of the pressure experienced nearly 1 kilometer beneath Earth's oceans. Any spacecraft sent there is swiftly crushed by this immense weight. The temperature at the surface reaches an almost constant 470 degrees Celsius, hotter than Mercury. Even though Mercury is closer to the Sun, this is the result of a runaway greenhouse effect, one of the most dramatic climate transformations known to planetary science. Long ago, Venus may have been very different. Many scientists believe that in the distant past it could have had liquid water, oceans, and a much milder climate, possibly even conditions suitable for life. But as solar radiation increased, surface temperatures rose. Water began to evaporate, and water vapor, itself a powerful greenhouse gas, intensified the warming. At the same time, intense volcanic activity released vast amounts of carbon dioxide into the atmosphere. With no effective mechanisms to remove this gas, it accumulated relentlessly, thickening the atmospheric blanket and trapping ever more heat. Over time, Venus transformed into the furnace we see today. Despite reflecting most sunlight, the dense carbon dioxide atmosphere absorbs and redistributes heat with extraordinary efficiency. As a result, temperatures remain almost uniform across the entire planet, with little difference between day and night, equator and poles. Even on the night side of Venus, where the sun does not shine, the same unbearable heat persists. The atmosphere itself circulates this energy like a colossal thermal engine. Beneath the clouds, Venus hides a surface both alien and strangely familiar. Because the thick atmosphere blocks visible light, scientists study the surface using radar imaging. What they have discovered is a world dominated by vast lava plains, shaped by immense volcanic eruptions in the planet's past. Venus appears to be one of the most volcanically resurfaced planets in the solar system. One of its highest regions, Maxwell Montes, rises to about 11 kilometers above the surrounding terrain, higher than Mount Everest on Earth. The surface is also marked by enormous circular structures called coronae, massive features formed by rising plumes of hot magma that bulged the crust upward and then collapsed. And like Earth, Venus shows no clear evidence of active plate tectonics. Instead of moving plates, its crust seems to bend, fracture, and periodically renew itself through catastrophic volcanic episodes. This creates a landscape shaped not by steady geological motion, but by sudden, planet-wide transformations. High above the surface, at an altitude of about 60 kilometers, Venus's atmosphere moves with astonishing speed. Winds there reach up to 360 kilometers per hour, a phenomenon known as atmospheric superrotation, where the atmosphere circles the planet far faster than the surface itself rotates. Venus has the slowest rotation of any planet in the solar system, One full day on Venus lasts 243 Earth days, even longer than its own year, which is only 225 Earth days. In other words, on Venus, a single day is longer than an entire year. Venus was among the first planets humans attempted to explore with spacecraft. The Soviet Venera missions achieved historic firsts by successfully landing probes on its surface. Instruments aboard Venera 7 and later landers transmitted data directly from the ground, surviving only 20 to 30 minutes before being destroyed by the extreme conditions. These brief moments, however, provided humanity's only direct measurements from the surface of Venus. Later, the European Space Agency's Venus Express mission studied the planet's atmosphere in great detail, revealing global wind patterns, chemical cycles, and mysterious changes in cloud structure. Today, new missions are being prepared to return to Venus. Projects such as NASA's Da Vinci and Veritas aim to plunge directly through the atmosphere and map the planet with unprecedented precision. Their goal is to uncover Venus's internal structure, volcanic history, and climatic evolution, and to finally answer one of the most haunting questions of planetary science: was Venus once a habitable world? And if so, what caused its irreversible downfall? Venus stands before us not only as a world of fire and sulfur, but also as a mirror of Earth's possible future. It reminds us that planetary climates can change forever, that balance is fragile, and that the line between life and total desolation can be crossed silently over millions of years. Next on our journey through the inner solar system, we arrive at our home world, Earth, the only planet we currently know that harbors life. Among all the worlds circling the Sun, Earth stands apart not by size or brightness, but by a rare and fragile miracle: liquid water. About 70% of Earth's surface is covered by oceans, seas, rivers, and lakes. Water is the foundation of all known life, and its extraordinary properties, high heat capacity, solvent power, and chemical flexibility make it the perfect medium for biological processes. But why does Earth have vast oceans while Venus became a furnace and Mars a frozen desert? The answer lies in Earth's position within the habitable zone, the narrow region around a star where temperatures allow water to exist in liquid form. If Earth were only slightly closer to the Sun, it might have suffered the same runaway greenhouse catastrophe as Venus. If it were farther away, it could have become a frozen wasteland like Mars. Life exists here because Earth occupies a precise, delicate balance between fire and ice. No less important is Earth's magnetosphere, the invisible magnetic shield that protects our planet from the violent forces of space. This magnetic field is generated by the movement of liquid iron within Earth's outer core. Acting like a vast cosmic barrier, it deflects the solar wind and much of the deadly cosmic radiation streaming through the solar system. Without this protective shield, Earth's atmosphere could have been stripped away over billions of years. Just as Mars lost most of its air and surface water, the solar wind itself is a continuous of charged particles ejected from the Sun's outer atmosphere, the corona. These particles race through space at speeds of up to 800 kilometers per second, sweeping across the solar system. When they interact with Earth's iosphere, they create one of nature's most breathtaking phenomena of auroras, the shimmering northern and southern lights. At the same time, the magnetosphere absorbs the destructive force of this radiation, preserving the atmosphere and shielding life on the surface. Earth is not a static world. It is a living, dynamic planet, constantly reshaping itself through the slow but relentless movement of tectonic plates. Earth's rigid outer crust is divided into massive plates that float atop the semi-liquid mantle below. These plates drift, collide, separate, and slide past one another. Their motion builds mountains, opens ocean basins, triggers earthquakes, and fuels volcanic activity. Plate tectonics plays a critical role in recycling chemical elements and regulating Earth's long-term climate. Carbon dioxide released by volcanoes enters the atmosphere, contributes to the greenhouse effect, and helps prevent the planet from freezing solid. Over geological time, this same carbon is later locked into rocks, completing a vast planetary breathing cycle. Volcanoes, though often associated with destruction, are also creators. They shape continents, build new land, and release gases that influence climate. Water vapor and carbon dioxide emitted during eruptions help form Earth's early atmosphere, while molten minerals enriched the surface and laid the foundation for soil and ecosystems. Without volcanism, Earth would be a cold, geologically dead world like many others in the solar system. Its atmosphere is another of its rare gifts. It consists of about 78% nitrogen, 21% oxygen, and small amounts of argon, carbon dioxide, and trace gases. This precise composition did not arise by chance. It is the result of billions of years of interaction between geology and life. Oxygen, now essential for complex organisms, was once almost completely absent. It began to accumulate around a point 4 billion years ago during the Great Oxygenation Event, when ancient microorganisms learned to harness sunlight through photosynthesis and released oxygen as a byproduct. This transformation altered the chemistry of the planet forever and opened the door to complex, multicellular life. Carbon dioxide, though present in relatively small quantities, plays a crucial role in regulating Earth's temperature through the greenhouse effect. It traps heat in the lower atmosphere, preventing Earth from becoming a frozen sphere. Yet this balance is extraordinarily fragile. Even small changes in the concentration of greenhouse gases can shift global temperatures dramatically. Venus stands as a permanent warning of what happens when this balance is lost forever. Earth's oceans, atmosphere, magnetosphere, plate tectonics, and stable climate together form a finely tuned system unlike any other we have ever observed. Life is not merely surviving on Earth, it is woven into the planet's very structure. Living organisms shape the atmosphere, influence the chemistry of the oceans, and even alter the composition of rocks. Earth and life have evolved together as a single, intertwined system for over 4 billion years. From space, Earth appears as a small blue sphere, fragile and luminous against the blackness of the cosmos. And yet within this thin layer of air and water exists everything humanity has ever known, every ocean and forest, every civilization and language, every triumph and tragedy. Earth is not just another planet in the solar system. It is a rare sanctuary of life in a universe that is otherwise vast, cold, and silent. The Moon is speaking about our home planet. It is impossible not to mention its silent and faithful companion, the Moon, more than just a beautiful light in the night sky. The Moon plays a vital role in the stability of Earth and in the very development of life itself. With a diameter of about 3,470 kilometers, it is the largest natural satellite in the solar system relative to the size of its parent planet. Its presence is not accidental. It is one of the key reasons why Earth became a stable, life-supporting world. First, the Moon stabilizes the tilt of Earth's axis. This tilt is responsible for the changing seasons and for the long-term stability of Earth's climate. Because of the Moon's gravitational influence, Earth's axial tilt remains relatively constant over millions of years. Without the Moon, Earth's axis could wobble chaotically, causing extreme and unpredictable climate shifts. Entire ecosystems could collapse as scorching heat and deep freezing alternated without rhythm. The gentle balance that allows forests, oceans, and civilizations to exist would be impossible. Second, the Moon is the master of tides. Its gravity pulls on Earth's oceans, creating the rhythmic rise and fall of sea levels across the planet. These tides shape coastlines, feed nutrient cycles in the oceans, and drive powerful ecological processes. Ancient tidal zones, where seawater regularly flooded and retreated, may have been the cradle of life's transition from ocean to land. In these constantly changing environments, early organisms learned to survive both in water and in air, laying the foundation for all terrestrial life that followed. Even today, countless species depend on lunar rhythms for reproduction, migration, and survival. Third, in the violent youth of the solar system, the moon acted as a cosmic shield. During the era of heavy bombardment, Earth and the moon were constantly struck by asteroids and comets. The moon absorbed a significant portion of these impacts, as its scarred, cratered surface clearly reveals. Without this silent guardian, Earth's surface might have been far more devastated, delaying or even preventing the emergence of stable environments suitable for life. The moon also influences Earth in more subtle ways. Its gravitational pull helps stir ocean currents, contributing to the global transport of heat and nutrients. It slows Earth's rotation over time, gently lengthening our days. Billions of years ago, a day on Earth lasted only a few hours. The moon's steady braking force gradually shaped the rhythm of daylight and night that all life now follows. For humanity, the moon has always been more than a scientific object. It has been a symbol of time, mystery, and meaning. Ancient civilizations measured months by its phases, built calendars around its cycle, and filled myths and legends with its silver light. In 1969, when humans first set foot on the moon, it became not only a symbol of dreams but also of scientific determination and technological achievement. Those first footprints marked the moment when a species born under the moon's influence finally reached its surface. Today, the moon continues to be a gateway to space. It may one day host scientific bases, observatories, and even stepping stones for journeys deeper into the solar system. By studying its rocks, we learn about the earliest history of Earth and the violent processes that shaped both worlds. In understanding the moon, we come to see not only its uniqueness but also the fragility of our cosmic home. Earth and the moon are bound together in a silent gravitational dance that has lasted billions of years. This partnership helped create the conditions for life, for oceans and seasons, for stability and change. And as we gaze at the moon in the night sky, we are reminded that even the smallest shifts in the balance of the cosmos can transform the destiny of entire worlds. Mars. The next world on our journey is Mars, our closest planetary neighbor. A silent witness to the ancient history of the solar system and perhaps a mirror of Earth's own distant past and possible future. Since antiquity, Mars has drawn the gaze of humanity. Its reddish glow in the night sky inspired myths of war, fire, and catastrophe. Yet today, Mars has come to symbolize not destruction, but hope. It is a world that may hold answers to one of humanity's oldest questions: are we alone in the universe? Mars is the fourth planet from the Sun, located at an average distance of about 228 million kilometers, or 1.52 astronomical units. Because of this greater distance, it receives far less warmth and sunlight than Earth. In size, Mars is roughly half the diameter of our planet. Yet its total surface area is almost equal to all the landmass of Earth combined. Its mass is only about 11% of Earth's mass, and its surface gravity is just 38% of what we experience here. A person weighing 70 kilograms on Earth would weigh only about 26 kilograms on Mars, moving as if in a slow, floating dream. Mars is a frozen desert world. The average temperature across the planet is around -63 degrees Celsius, but this varies dramatically with location and season, dropping to -125 degrees at the poles in winter, and rising up to 20 degrees at the equator during summer days. These extreme fluctuations are caused by Mars' thin atmosphere, which is unable to retain heat. The atmospheric pressure on Mars is less than 1% of Earth's, comparable to conditions more than 30 kilometers above Earth's surface, far higher than commercial aircraft ever fly. The atmosphere itself consists of about 96% carbon dioxide, with small traces of nitrogen, argon, oxygen, and water vapor. One of the most striking features of Mars is its planet-wide dust storms. Fine reddish dust can rise into the atmosphere and cover the entire planet for months, blocking sunlight and plunging temperatures. One such storm in 2018 was so powerful that it ended the long mission of the rover Opportunity, which had worked on Mars for over 14 years. These storms remind us how active and unpredictable this seemingly silent world can be. Yet beneath its barren appearance, Mars is a planet of extraordinary geological wonders. Vast deserts of oxidized iron, ancient river valleys, giant volcanoes, and frozen polar ice caps tell the story of a world that may once have been far more alive. Towering above everything stands Olympus Mons, the largest volcano in the solar system, rising 22 kilometers high, nearly 3 times the height of Mount Everest. Its base is so vast that a human standing at its foot would not even see its summit because of the planet's curvature. Stretching across the surface is also Valles Marineris, a colossal canyon system over 4,000 kilometers long and up to 7 kilometers deep, dwarfing Earth's Grand Canyon in both length and depth. But the greatest mystery of Mars is water. Today, liquid water cannot exist on the surface due to low pressure and temperature. Yet everywhere we look, we find clear evidence that billions of years ago Mars was once warm and wet. Dry riverbeds, delta formations, and sedimentary rocks all suggest that rivers once flowed. Lakes filled vast basins, and perhaps even an ocean covered much of the northern hemisphere. As Mars cooled and its magnetic field weakened, its atmosphere was slowly stripped away by the solar wind, and liquid water vanished from the surface. Today, water survives only as ice in the polar caps, frozen within the soil, and possibly as liquid reservoirs deep beneath the southern polar ice, where radar has detected what may be underground lakes. These discoveries fuel the most powerful question of all: could life have once existed on Mars, and could traces of it remain today? To seek answers, humanity has sent an armada of robotic explorers. The rover Curiosity, operating since 2012, confirmed that ancient Mars had conditions suitable for microbial life. The rover Perseverance, which arrived in 2020, now explores the Jezero crater, once a lake with a river delta, one of the most promising locations for preserving ancient biosignatures. It drills into rocks, seals samples, and prepares them for potential return to Earth in future missions. Mars is no longer just an object of study, it is becoming a destination. Space agencies and private companies alike dream of sending humans to its surface within the coming decades. Visions of future explorers stepping onto the rust-colored plains, building the first shelters beneath an alien sky, and transforming science fiction into reality now feel closer than ever before in human history. Mars stands before us as both a warning and an invitation. It shows us what can happen when a planet loses its atmosphere, its oceans, and its protective magnetic shield. Yet it also invites us to explore, to learn, and to expand the boundaries of human presence beyond Earth. And as we turn our gaze once more toward the outer giants of the solar system, our next destination rises into view: Jupiter, the giant king of planets, whose immense gravity commands the rhythm of worlds far beyond the reach of Mars. Jupiter. Now we leave the realm of rocky worlds behind and enter the domain of the giants. Between Mars and Jupiter stretches the asteroid belt, a vast region filled with millions of rocky and metallic fragments that never united into a full-sized planet. Scientists believe that Jupiter's immense gravity prevented these objects from ever forming a world, tearing them apart before they could grow. And beyond this restless belt rises the true ruler of the solar system after the Sun itself, Jupiter. The largest and most powerful planet of them all. Jupiter is so enormous that more than 1,000 Earths could fit inside it. Its influence reaches far beyond its visible size. This gigantic world acts as a cosmic guardian, drawing asteroids and comets toward itself and away from the fragile inner planets. Many scientists believe that without Jupiter's gravitational protection, Earth would have suffered far more catastrophic impacts throughout its history. In this sense, Jupiter has quietly shaped the destiny of life on our planet. Jupiter is a world of endless storms, crushing pressure, and overwhelming magnetism. It is impossible to imagine this planet without its swirling clouds, violent hurricanes, colossal radiation belts, and its famous eternal tempest, the Great Red Spot. Jupiter's mass is more than 318 times that of Earth, and its gravity is about 2.5 times stronger than Earth's. If a human could somehow stand within Jupiter's atmosphere, their weight would instantly multiply, though no solid surface exists beneath their feet. Jupiter has no true surface at all. It is a world made almost entirely of hydrogen and helium, much like the Sun itself. As we descend through Jupiter's atmosphere, we pass through vast layers of colorful clouds filled with ammonia, methane, and water vapor. Winds roar at speeds of up to 600 kilometers per hour, sculpting the planet's iconic light and dark bands. Deeper below, the pressure becomes so intense that hydrogen is forced into a liquid state, and then into something even more extraordinary, metallic hydrogen. This exotic ocean, tens of thousands of kilometers deep, behaves like an electrical conductor. It is here, within this churning sea of metallic hydrogen, that Jupiter's immensely powerful magnetic field is born. At the very heart of Jupiter, hidden beneath unimaginable pressure, may lie a small rocky core roughly 10 times the mass of Earth, or perhaps it has already dissolved into the surrounding metallic ocean. Even today, scientists continue to debate the true structure of Jupiter's interior. The conditions there can never be reproduced fully on Earth. Jupiter's atmosphere is a living, boiling ocean of gas. Monster storms swirl endlessly through its clouds. Lightning flashes thousands of times more powerful than anything on Earth. Pressure in the lower layers becomes so extreme that gases turn into liquids. And towering above all its storms is the legendary Great Red Spot, a hurricane that has raged without interruption for at least 350 years. Its diameter today is about 16,000 kilometers, wide enough to swallow the Earth whole. Once even larger, the storm has slowly been shrinking, though no one knows whether it will one day vanish or continue forever. Jupiter's magnetic field is the strongest of any planet in the solar system, more than 20,000 times stronger than Earth's. Its magnetosphere stretches millions of kilometers into space. If we could see it with our eyes, it would appear larger in the night sky than the full moon. Within this colossal magnetic bubble, radiation levels become deadly even to heavily shielded spacecraft. This violent environment forces missions like Juno to follow carefully calculated orbits, diving in close and quickly retreating before radiation can destroy their instruments. But Jupiter is not only a planet. It is the center of an entire system of worlds. More than 80 moons circle this giant, and among them are the 4 famous Galilean moons: Io, Europa, Ganymede, and Callisto. Each of these moons is a world in its own right. Io is a realm of fire. It is the most volcanically active object in the solar system. Its surface is constantly being reshaped by huge eruptions that hurl sulfur and molten rock hundreds of kilometers into space. Its interior is heated by the relentless gravitational tug-of-war between Jupiter and neighboring moons. Europa is a world of ice and hidden oceans. Beneath its cracked, frozen surface lies a vast global ocean of liquid water, an ocean that may contain more water than all of Earth's oceans combined. Tidal forces from Jupiter warm this ocean and keep it from freezing solid. Jets of water vapor erupt from the surface into space. If life exists anywhere beyond Earth in our solar system today, Europa is one of the most promising candidates. Ganymede, The largest moon of all is even bigger than the planet Mercury. It possesses its own magnetic field, a rare and astonishing feature for a moon. Beneath its icy shell may also lie a hidden subsurface ocean. Callisto is an ancient, heavily cratered world, one of the oldest surfaces in the solar system. Its battered appearance preserves a record of the violent early history of planetary formation. And even here, beneath the frozen crust, scientists suspect there may be a concealed ocean of water. Jupiter was first visited at close range by the Pioneer and Voyager missions in the 1970s, which revealed its immense power and complexity. In the 1990s, the Galileo spacecraft deepened our understanding of its atmosphere and moons. Today, the Juno mission continues to explore Jupiter's deep structure and magnetic field. And in the coming decades, the JUICE mission will focus on Europa, Ganymede, and Callisto, searching for signs that life could exist beneath their icy shells. Jupiter is not just a planet. It is a solar system within a solar system, a colossal engine of gravity, storms, radiation, and hidden oceans. It shapes the orbits of worlds, deflects cosmic threats, and guards secrets that may one day reshape our understanding of life itself. And beyond Jupiter, even greater mysteries still await us among the distant giants of the outer solar system. Saturn. Jupiter may be the king of the planets by sheer power and mass, but its neighbor Saturn is no less astonishing. If Jupiter is a cosmic ruler, then Saturn is its elegant aristocrat, a world of breathtaking beauty. Surrounded by the most magnificent ring system in the entire solar system and accompanied by moons that seem drawn from pure science fiction. After the colossal gravity of Jupiter, our path now leads further outward to this serene and mysterious giant, whose appearance alone has fascinated humanity for centuries. Saturn is the second largest planet in the solar system. Its diameter is more than 9 times greater than Earth's, yet despite its enormous size, it is the least dense of all the planets. Its average density is so low that, in theory, if there were a vast enough ocean, Saturn could actually float upon it. Of course, such an ocean does not exist, but this simple image captures just how light and gas-filled this world truly. Like Jupiter, Saturn is composed primarily of hydrogen and helium, layered into immense bands of clouds and deep atmospheric currents. But Saturn's true signature, the feature that makes it instantly recognizable, is its majestic ring system. From afar, the rings appear as a smooth, solid disk encircling the planet. In reality, they are made of billions upon billions of individual particles, fragments of ice and rock ranging from tiny grains of dust to blocks as large as houses. These countless fragments move in precise orbits, forming a vast, flattened disk. Although the rings stretch hundreds of thousands of kilometers wide, their average thickness is astonishingly small, only about 10 meters. Seen from the side, they almost vanish into nothingness. The origin of Saturn's rings remains one of astronomy's great puzzles. Some scientists believe they may be the remains of a former moon that wandered too close to Saturn and was torn apart by its powerful gravity. Others suggest the rings are primordial material that never managed to form a moon in the first place. Within this dazzling system lie curious structures, such as the Cassini division, a dark gap nearly 4,800 kilometers wide, separating the rings into major sections. This gap is maintained by the gravitational influence of Saturn's moon Mimas, which sweeps particles out of this orbital region like an invisible sculptor. Saturn's atmosphere, like Jupiter's, is composed mainly of hydrogen and helium, tinted with trace gases that give its clouds a soft golden hue. And while Jupiter is famous for its great red spot, Saturn possesses an atmospheric marvel of its own, the hexagonal storm at its north pole. This colossal structure has the shape of a perfect geometric hexagon, stretching nearly 25,000 kilometers across. Inside this vast formation, Winds roar at speeds exceeding 500 kilometers per hour, yet the edges of the hexagon remain sharply defined, as if drawn with a ruler. Decades after its discovery, scientists still do not fully understand why this storm takes such an extraordinary shape. Saturn's atmosphere also undergoes dramatic global changes. In 2010, its northern hemisphere suddenly shifted in color from bluish tones to warm gold. This transformation occurred as sunlight returned after a long Saturnian winter. Ultraviolet radiation triggered photochemical reactions in the atmosphere, breaking down compounds that had once absorbed red light and revealing the planet's natural yellow hues beneath. Yet Saturn is not defined by its rings and clouds alone. It is also the lord of a vast family of 83 known moons, among which several stand as worlds of profound scientific importance. Among them, Titan shines as one of the most extraordinary moons in the solar system. Titan is the second largest moon after Ganymede, and it is even larger than the planet Mercury. What makes Titan truly unique is its dense atmosphere, the only moon known to possess one thick enough to resemble a planetary sky. On Titan, the sky glows with a deep orange haze. The surface stretches across frozen plains of water ice as hard as rock. And most remarkably of all, rain falls on Titan, but not rain of water. Instead, clouds release liquid methane and ethane, which form rivers, lakes, and even seas. At Titan's surface temperature of around -180 degrees Celsius, water is frozen solid, while hydrocarbons flow like earthly water. Titan has seasons, changing weather, and an active climate cycle astonishingly similar in structure to Earth's. Despite its alien chemistry, even more intriguing, beneath Titan's icy crust, scientists believe there may exist a subsurface ocean of liquid water. If this hidden ocean truly exists, it may contain the conditions necessary for life, making Titan one of the most promising locations in the search for biology beyond Earth. Another moon of Saturn, Enceladus, astonished scientists with its unexpected activity. Though only about 500 kilometers in diameter, this small moon ejects powerful plumes of water vapor and ice particles from fractures near its south pole. These geysers are so strong that their particles help form one of Saturn's faint outer rings. Beneath Enceladus's surface lies a global ocean of liquid water in contact with a rocky core. Within this ocean, scientists have detected organic molecules and chemical energy sources, conditions that resemble the basic ingredients needed to sustain life. Alongside Europa, Enceladus stands among the strongest candidates in the solar system for hosting extraterrestrial life. Our most detailed understanding of Saturn and its moons comes from the long-lived Cassini-Huygens mission. Launched in the late 1990s, it explored the Saturnian system for 13 years, sending back an endless stream of breathtaking images and priceless scientific data. The Huygens probe, which separated from Cassini, became the first spacecraft to land on a moon in the outer solar system when it touched down on Titan's surface. It revealed river channels, icy stones, and landscapes shaped by liquid hydrocarbons. In 2017, Cassini ended its mission with a final, deliberate descent into Saturn's atmosphere, transmitting measurements until the last moment before being consumed by the planet it had studied for over a decade. Saturn marks the outer boundary of the classical gas giants. Beyond it lie Uranus and Neptune, distant, icy worlds of extreme winds, tilted axes, and hidden oceans beneath frozen crusts. As we leave Saturn behind, with its glowing rings and strange, life-hinting moons, we move farther into the cold frontier of the solar system, where even colder and darker mysteries await. Uranus. After leaving behind the glowing rings and mysterious moons of Saturn, our journey carries us farther into the deep, silent realms of the solar system, into the domain of the ice giants. Here, in the cold outer darkness, we encounter Uranus, the seventh planet from the Sun. Though smaller than Jupiter and Saturn, Uranus captivates scientists with its profound strangeness. It is a pale blue world that seems to defy nearly every planetary rule of a planet that spins on its side, wrapped in faint rings and accompanied by moons shaped by violent ancient forces. Beneath its calm appearance lies a realm of extreme cold, powerful winds, and hidden internal heat that remains largely unexplored, and like Jupiter and Saturn, which are dominated by hydrogen and helium, Uranus belongs to a different class of worlds, the ice giants. This does not mean that Uranus is made of solid ice, but rather that its interior contains vast amounts of water, ammonia, and methane compressed into dense, exotic states. If one could descend into Uranus, they would first pass through a frigid upper atmosphere of hydrogen, helium, and methane. Deeper still, these gases would become increasingly dense, transitioning into enormous layers of superheated ices under immense pressure. There is no solid surface on which to stand. The planet gradually shifts from gas to liquid to superdense fluid. At its center, scientists believe a small rocky core exists, roughly comparable in mass to Earth, buried beneath a thick mantle of hot, pressurized ice. Temperatures inside Uranus may exceed 5,000 degrees Celsius, yet this internal warmth barely escapes into space. And this leads to one of Uranus's greatest mysteries. Despite its internal heat, Uranus is the coldest planet in the solar system. Average atmospheric temperatures plunge to about -224 degrees Celsius, even colder than those of the more distant Neptune. The reason is still uncertain, but unlike other giant planets, Uranus releases almost no internal heat. It is as if its inner furnace were somehow shut behind thick, frozen walls. The most astonishing feature of Uranus, however, is its extreme axial tilt. While most planets spin upright like a top, Uranus is tilted by about 98 degrees. It does not merely lean, it effectively rolls along its orbit. For half of its 84-year-long orbit, one of its poles faces the sun continuously, bathing in decades of unbroken daylight. Then, for the next half of the orbit, that same pole plunges into 42 years of total darkness. This produces the most extreme seasons anywhere in the solar system. Scientists believe this bizarre tilt was caused by a colossal collision early in Uranus's history, perhaps with an object as large as a young planet, a cosmic impact that permanently knocked Uranus onto its side. Although Uranus looks calm and serene from afar, its atmosphere is anything but peaceful. It is composed mainly of hydrogen and helium, with about 2% methane, the gas responsible for Uranus's haunting blue color. Methane absorbs red light from the sun while reflecting blue-green wavelengths back into space. Powerful winds race through the upper atmosphere at speeds approaching 900 kilometers per hour, forming shifting cloud bands and enormous storm systems that emerge and fade over the long Uranian seasons. Uranus is also encircled by a system of dark, narrow rings. They are far thinner and dimmer than Saturn's, made of particles that reflect very little light. These rings may be the shattered remains of ancient moons that were torn apart by Uranus's gravity. Yet the planet's greatest wonders may lie among its moons. Among Uranus's many satellites, Miranda stands as one of the most extraordinary objects ever discovered. Its small surface is scarred with gigantic cliffs, deep chasms, and fractured terrain so violent that it resembles a world that has been broken and reassembled. Some of Miranda's canyons plunge deeper relative to its size than Earth's Grand Canyon. Scientists suspect that Miranda may once have been shattered by a catastrophic collision, only for its fragments to slowly reassemble under gravity into the chaotic body we see today, a fossil of unimaginable cosmic violence. Remarkably, only one spacecraft has ever visited Uranus up close. In 1986, Voyager 2 swept past the planet, capturing the first and only close-range images of its pale atmosphere, dark rings, and strange moons. Since that fleeting encounter, Uranus has remained a distant, cold enigma. No other probe has yet returned, but plans for future missions are taking shape. Space agencies are discussing sending a new orbital spacecraft to Uranus in the 2030s. one that could finally uncover the secrets of its interior, its magnetic field, its frozen moons, and its long, shadowed seasons. Uranus is a planet of quiet mysteries, cold, distant, tilted against the cosmic order. It reminds us that the solar system is not built upon uniform laws alone, but also upon ancient collisions, hidden forces, and slow transformations that continue across billions of years. And beyond Uranus, even darker and stormier realms await, where Neptune, the last great giant, reigns over the outer frontier of our Sun's domain. Neptune. After the silent, tilted mystery of Uranus, our journey reaches the last of the great giants of the solar system, Neptune. This is the most distant of the 8 planets, the cold frontier where sunlight weakens and the power of the sun fades into a pale glow. Even today, despite modern telescopes and advanced computer models, Neptune remains one of the least explored and most enigmatic worlds in our system. At first glance, it resembles Uranus, the deep blue sphere wrapped in clouds. But this similarity is deceptive. If Uranus is a quiet, frozen world, then Neptune is a realm of relentless cosmic storms, the true master of solar winds and atmospheric violence. Neptune, like Uranus, belongs to the class of ice giants. Its atmosphere is composed primarily of hydrogen and helium, with a significant presence of methane, which gives the planet its rich blue color by absorbing red light and reflecting blue. Yet what truly sets Neptune apart is not its color, but its extraordinary winds. Neptune holds the record for the strongest winds in the entire solar system. Atmospheric speeds here can reach up to 2,400 kilometers per hour, faster than the speed of sound on Earth, and more powerful than any hurricane ever observed on our planet. These winds tear through the upper atmosphere, driving colossal storm systems across the globe. What makes this even more mysterious is the fact that Neptune receives only a tiny fraction of the sunlight that reaches Earth, about 1/900th of what Jupiter receives. Its upper clouds should be calm and frozen, yet deep below, the planet radiates twice as much heat as it receives from the sun. This powerful internal energy source fuels its violent winds and constant atmospheric upheaval. The precise mechanism behind this internal heat remains one of the great unsolved questions of planetary science. In 1989, when the spacecraft Voyager 2 made its historic flyby, Neptune revealed one of its most famous features, the Great Dark Spot. This vast storm system, similar in appearance to Jupiter's Great Red Spot, stretched across thousands of kilometers. Winds within it reached nearly 2,000 kilometers per hour. But like Jupiter's ancient storm, Neptune's dark vortex proved temporary. When astronomers later pointed the Hubble Space Telescope toward Neptune, the Great Dark Spot had vanished. It had simply dissolved. Since then, new dark storms have been observed forming and disappearing every few years. Neptune is the only planet where giant storms are born and destroyed on human timescales, making its atmosphere the most dynamic of all. Like all the giants, Neptune has no solid surface. Anyone attempting to descend into its atmosphere would pass through ever-thickening layers of gas, then into super-dense fluids, until pressure and temperature became instantly fatal. Beneath the blue clouds lies a massive icy mantle, composed of superheated water, ammonia, and methane compressed into exotic states of matter unknown on Earth. At Neptune's core, hidden beneath these layers, is believed to be a dense, rocky, Earth-like, where temperatures may reach 7,000 degrees Celsius. This hidden furnace helps drive the planet's astonishing wind speeds and storm activity. Among Neptune's moons, one stands apart in both size and strangeness: Triton. Triton is the planet's largest satellite, and one of the most unusual objects in the solar system. And like most moons, which orbit in the same direction as their planet's rotation, Triton moves in the opposite direction. This inverted orbit tells astronomers that Triton was not born with Neptune. Instead, It was likely captured long ago from the distant Kuiper Belt, a vast region of frozen worlds beyond Neptune's orbit. Triton is a world of deep cold and hidden fire. Its surface is covered in nitrogen ice, and its temperature drops to around -235 degrees Celsius, making it one of the coldest places known. Yet despite this extreme cold, Voyager 2 discovered active cryovolcanoes on Triton, geysers that erupt nitrogen gas and ice particles kilometers into space. These eruptions reveal that Triton still possesses internal heat. Beneath its frozen crust, scientists suspect the existence of a subsurface ocean of liquid water, similar to those believed to exist on Europa and Enceladus. If so, Triton 2 could be a potential refuge for extraterrestrial life hidden far beneath the ice. To this day, Voyager 2 remains the only spacecraft ever to visit Neptune. Since that fleeting encounter, Neptune has remained distant and largely untouched. In recent years, astronomers have proposed new missions, including potential orbiters and specialized probes like conceptual projects aimed at returning to Neptune and directly investigating Triton's hidden ocean. Yet such missions would take decades. Even if a spacecraft were launched in the coming years, it would not reach Neptune until the 2040s or later. With Neptune, our journey through the 8 major planets of the solar system reaches its end. Yet the solar system itself does not truly end here. Beyond Neptune stretches the vast, shadowed realm of the Kuiper Belt, a distant ring filled with thousands of frozen worlds including Pluto, Haumea, Makemake, and countless other icy bodies. And beyond even that lies the distant Oort cloud, a spherical halo of ancient debris marking the very edge of the Sun's gravitational kingdom, though small compared to the giants. These minor worlds of asteroids, comets, dwarf planets, and meteoroids carry within them the memory of the solar system's birth. They preserve the original building blocks from which the planets arose, and some still wander dangerously close to Earth, reminding us that the story of cosmic creation is not only ancient, but ongoing. Asteroids. When astronomers first began to systematically explore the night sky, they expected to find another full-size planet between Mars and Jupiter. According to early mathematical patterns of planetary spacing, a large world seemed destined to exist in that empty region. But instead of a single planet, scientists discovered something far more intriguing: the asteroid belt. A vast zone filled with millions of rocky fragments that never managed to merge into a true planet. This belt arose billions of years ago during the chaotic birth of the solar system. As young planets were forming from swirling gas and dust, Jupiter's immense gravity disrupted the material in this region, preventing it from coalescing into one stable body. The result is a cosmic graveyard of unfinished worlds of asteroids, ranging in size from tiny pebbles to massive objects hundreds of kilometers across. Among the largest is Vesta, a giant of the belt measuring about 525 kilometers in diameter, nearly large enough to be considered a minor planet in its own right. Asteroids are incredibly diverse in composition. Some are rich in metals, especially iron and nickel. Others are dominated by silicate rock, while a third group contains large amounts of carbon-based compounds and even traces of water-locked-in minerals. These ancient fragments are time capsules from the earliest era of planet formation, preserving pristine material unchanged for more than 4.5 billion years. By studying them, scientists gain direct insight into the conditions that shaped the young solar system and the ingredients that eventually gave rise to Earth. Yet asteroids are not only objects of scientific wonder, they also represent a real and persistent danger. We know that 66 million years ago, a massive asteroid struck our planet near what is now the Yucatan Peninsula. The resulting impact triggered global fires, tsunamis, and a prolonged climate collapse that led to the extinction of the dinosaurs and reshaped the course of life on Earth. This single event stands as a powerful reminder that the solar system is not a static, harmless place. Today, astronomers closely monitor near-Earth objects, asteroids whose orbits can bring them close to our planet. Most of the large ones are well tracked and pose no immediate threat. However, smaller bodies, often only tens or hundreds of meters wide, are far more difficult to detect and can still cause catastrophic regional damage if they strike. For this reason, planetary defense has become a serious scientific priority. In 2022, humanity took its first practical step toward protecting the planet when NASA's DART mission successfully altered the orbit of a small asteroid by deliberately crashing the spacecraft into it. This historic experiment proved that, with enough preparation, we are no longer completely powerless against cosmic impacts. For the first time in Earth's history, intelligent life demonstrated its ability to nudge the course of celestial bodies not for conquest, but for survival. Asteroids thus stand at a crossroads between past and future. They are the relics of planetary creation, the messengers of deep cosmic time, and at the same time, silent travelers whose paths occasionally intersect with our own. They remind us that Earth exists within a dynamic, ever-moving system where creation and destruction remain forever intertwined. Pluto. For a long time, Pluto was considered the ninth planet of the solar system. Discovered in 1930, it held a special place in both science and the public imagination for most of the 20th century. But in 2006, astronomers officially changed its status, reclassifying Pluto as a dwarf planet. This decision sparked worldwide debate and even emotional reactions for many people. Pluto had always been a true planet. Why, then, was it demoted? The answer lies in the modern scientific definition of a planet. According to the rules adopted by the International Astronomical Union, a planet must not only orbit the Sun and be nearly spherical in shape, it must also dominate its orbital neighborhood, clearing nearby space of other large bodies. Pluto does not meet this final criterion. Its orbit is shared with countless frozen objects of similar size, including Haumea, Makemake, and Eris, which in fact is slightly more massive than Pluto itself. All of these worlds belong to the vast and distant Kuiper Belt, a colossal region beyond Neptune filled with icy remnants from the formation of the solar system. Yet, the loss of planetary status has not diminished Pluto's scientific importance. On the contrary, it has become even more fascinating as a representative of an entirely new class of worlds. Pluto is a frozen realm of extreme contrasts, where surface temperatures plunge to about 230 degrees Celsius. Despite the brutal cold, its landscape is astonishingly complex and active. When NASA's New Horizons spacecraft flew past Pluto in 2015, it revealed a world far more dynamic than anyone had imagined. Pluto's surface is covered with vast icy plains of nitrogen, towering mountains of solid water ice, and signs of cryovolcanism, of volcanoes that erupt not with molten rock, but with slush-like mixtures of water, ammonia, and other frozen compounds. One of its most famous features is the enormous heart-shaped region known as Tombaugh Regio, a plain of nitrogen ice that slowly circulates like a frozen ocean. This discovery transformed Pluto from a distant point of light into a living, evolving world. Pluto also possesses a remarkable system of 5 moons, the largest of which, Charon, is so massive relative to Pluto that the two bodies form a true binary system, orbiting a shared center of mass located in the empty space between them. Charon is nearly half the size of Pluto itself, an extraordinary proportion that makes their relationship unlike that of any other planet-moon pair in the solar system. Together, they dance through the darkness as a gravitational duet, locked in eternal mutual rotation. Pluto's thin atmosphere adds yet another layer of mystery. Though extremely tenuous, it expands and contracts as the dwarf planet moves along its elongated orbit, sometimes freezing and falling back onto the surface as snow. This fragile atmosphere consists mainly of nitrogen with traces of methane and carbon monoxide, creating delicate blue hazes that shimmer above the horizon in the faint sunlight of the outer solar system, once dismissed as a cold, inactive leftover. Pluto has proven to be a world of hidden motion, geological youth, and quiet transformation. It marks the gateway to the distant frontier of the Kuiper Belt, a region where countless frozen worlds drift in eternal night, holding clues to the earliest stages of planetary formation, though no longer called a planet in the formal sense. Pluto remains a symbol of discovery itself, a reminder that the universe often defies our expectations, and that even the smallest worlds can reshape our understanding of the cosmos. Comets. When the New Horizons probe flew past Pluto in 2015, it sent back images that astonished scientists. That tiny, distant world turned out to be far more complex and alive than anyone had expected. But beyond Pluto lies an even vaster and more mysterious frontier, the realm of comets, the ancient wanderers of the solar system. If asteroids are mostly made of stone and metal, then comets are something entirely different. They are often called dirty snowballs, enormous masses of frozen water, carbon dioxide, ammonia, methane dust, and organic molecules. These cosmic relics have remained almost unchanged since the birth of the solar system more than 4.5 billion years ago, preserving within them the original material from which the planets were formed for most of their existence. Comets travel through the cold darkness of the outer solar system. But when one of them approaches the sun, everything changes. Under the intense heat, the frozen surface begins to evaporate, releasing gas and dust into space. A glowing cloud, the comet, forms around the nucleus, and from it grow one or several long, luminous tails. These tails can stretch for millions of kilometers, yet they are incredibly thin and fragile. One of the most remarkable features of a comet is that its tail always points away from the sun. This happens because the tail is shaped by the solar wind, a powerful, continuously streaming outward from the sun and sweeping cometary material into long luminous streams. Often, comets form two distinct tails, one made of dust, curved and soft, and another of ionized gas, straight and whisper thin, glowing in shades of blue. Comets come to us from two vast and distant regions of the solar system. The first is the Kuiper Belt, a broad disk of icy bodies beyond Neptune. From here arrive the short-period comets, which return regularly, sometimes every few decades. The most famous of them is Halley's Comet, which passes near the Sun every 76 years and has been observed by human civilizations for over 2,000 years. The second and far more remote source is the Oort cloud, a gigantic spherical shell of frozen objects stretching almost a light year from the Sun. This invisible reservoir contains trillions of dormant comets. Occasionally, a passing star or gravitational disturbance knocks one of them inward, sending it on a vast journey toward the inner solar system. These travelers become the long-period comets, appearing once in thousands or even millions of years. One of the most spectacular sights of the late 20th century was Comet Hale-Bopp, which illuminated the sky in 1997. For many months, with a tail visible even from brightly lit cities, comets may have played a crucial role in the history of life on Earth. Many scientists believe that during the early bombardment of the young planet, comets delivered enormous quantities of water. Along with water, they may also have transported organic molecules, the chemical building blocks of life itself. In this sense, every ocean, every drop of rain, and perhaps even life as we know it may carry within it the ancient signature of cosmic travelers. Closely related to comets are meteoroids, small fragments of rock or ice left behind by comets and asteroids. When these tiny particles plunge into Earth's atmosphere, they burn up in a flash of light, creating the familiar phenomenon of a shooting star. Most are no larger than grains of sand and never reach the ground. But occasionally, much larger fragments survive. The fiery descent. One of the most striking recent examples was the Chelyabinsk meteor in 2013. Space rock about 20 meters in diameter entered Earth's atmosphere at tremendous speed, exploding high above the city. The resulting shock waves shattered windows across a wide area and injured more than 1,000 people, a powerful reminder that the solar system remains a dynamic and sometimes dangerous place. And now, as our journey through the planets draws to a close, from the scorched surface of Mercury to the frozen winds of Neptune, from vast gas giants to distant icy worlds, we begin to understand something profound. Everything we have seen exists thanks to one central source. Without it, there would be no warmth, no light, no orbits, and no life itself. At the heart of this grand cosmic clockwork shines the sun, the star that binds the solar system together and gives meaning to every world that dances around it. Structure and processes of the sun. The sun is not merely a hot glowing sphere in the sky. It is a vast, complex, and dynamic world, a colossal nuclear engine whose processes shape the entire solar system. Its mass accounts for almost 99% of the total mass of the entire system. All planets, moons, asteroids, and comets together weigh less than 1/100th of the sun itself. Without it, there would be no orbits, no light, no warmth, and no life. But what exactly is this enormous star made of? What happens deep inside it? And how does it influence everything around it? At first glance, the sun seems like a solid disk of fire. In reality, it consists of several distinct layers, each playing a unique role in the production and transfer of energy. Everything begins in the core, the true heart of the sun. Here, at temperatures reaching 15 million degrees Celsius and under pressures billions of times greater than those on Earth, nuclear fusion takes place. In these extreme conditions, hydrogen atoms collide and merge, forming helium and releasing an unimaginable amount of energy. Every second, the sun converts millions of tons of matter into pure energy, following Einstein's famous equation. This is the source of all the light and heat that sustain life on Earth. Surrounding the core lies the radiative zone. In this vast region, energy no longer moves through violent collisions, but slowly migrates outward in the form of radiation. Photons born in the core begin an incredible journey through this layer, a journey that can take tens of thousands, sometimes even millions of years before they reach the surface. Here, the sun is quiet in appearance but relentless in its slow, patient transfer of energy. Above it lies the convective zone, where the mode of energy transport dramatically changes. Here, hot plasma rises toward the surface while cooler material sinks downward, forming enormous circulating currents, much like boiling water in a pot. These powerful convection flows shape the sun's visible texture and give rise to the cellular patterns known as granulation. They are also responsible for transporting magnetic fields and driving surface activity. The layer we actually see from Earth is the photosphere, an incredibly thin shell by cosmic standards, only about 500 kilometers thick. Yet this delicate boundary is what floods the solar system with light. Its temperature is about 5,500 degrees Celsius, relatively cool compared to the inferno of the core, but still hot enough to glow brilliantly. Dark regions known as sunspots appear here, cooler areas shaped by intense magnetic fields that suppress heat from rising below. Above the photosphere lies the chromosphere, a luminous reddish layer visible during solar eclipses. And beyond it stretches the corona, the sun's outer atmosphere. The corona extends millions of kilometers into space and is mysteriously far hotter than the layers below it, reaching temperatures of over 1 million degrees. From this ghostly halo, the Sun continuously releases charged particles into space, shaping the environment of the entire solar system. The Sun is a living, restless star. Deep within its core, fusion reactions transform hydrogen into helium every second, generating energy equivalent to the detonation of billions of hydrogen bombs each moment. This delicate balance between gravitational collapse and nuclear pressure has allowed the Sun to shine steadily for about 4.6 billion years, and it will continue to do so for billions more. Yet the Sun is not always calm. From time to time, colossal eruptions tear across its surface. Solar flares are sudden, powerful releases of energy that accelerate particles to near light speeds. Even more dramatic are coronal mass ejections, in which billions of tons of solar plasma are hurled into space at hundreds of kilometers per second. When such storms are directed toward Earth, they can trigger magnetic disturbances, disrupt satellites, endanger astronauts, interfere with radio communications, and even damage electrical grids on the ground. These cosmic storms remind us that space is not silent or serene, it is charged with powerful forces. The Sun influences the entire solar system through three fundamental mechanisms. The first is gravity. The Sun's gravitational pull binds all planets to their orbits. Without it, the solar system would immediately disintegrate into chaos, and every world would drift into the cold depths of interstellar space. The second is radiation. Sunlight warms Earth, drives weather systems, powers photosynthesis, and sustains every known form of life. Without this continuous flow of energy, our planet would quickly become a frozen, lifeless world. The third is the solar wind, a constant stream of charged particles flowing outward in all directions. This invisible wind sculpts planetary magnetospheres, strips atmospheres from some worlds, and creates breathtaking polar auroras on Earth and other planets. Far beyond the orbit of Pluto, the solar wind eventually collides with the interstellar medium at the boundary known as the heliopause, the true edge of the Sun's domain. More than 20 billion kilometers away, the Sun was born about 4.6 billion years ago from the collapse of a giant cloud of gas and dust. One day, it will also die. In about 5 billion years, its fuel will begin to run out. The core will contract, the outer layers will expand, and the Sun will become a red giant, swelling outward to engulf Mercury, Venus, and possibly even Earth. In its final stage, it will shed its outer layers into space, leaving behind a dense white dwarf, a faint stellar remnant, the silent core of what was once a radiant star. But that distant future lies billions of years ahead. For now, the Sun remains our eternal flame, the unwavering heart of the solar system, the silent engine that governs the rhythms of worlds and sustains life on our fragile planet. Without it, nothing we know could exist, and with it, the cosmic dance continues. We began our journey through the solar system by exploring the planets one by one, but now it becomes clear that everything within it is inseparably connected. This is not merely a collection of worlds drifting through space, it is a vast, living, dynamic system where every planet, every moon, every distant asteroid, and wandering comet is bound together by invisible threads of gravity, radiation, and the immense energy of our star. The solar system is a delicate cosmic mechanism, perfected over billions of years, where even the smallest motion resonates across enormous distances. Thank you for joining me on this incredible voyage through the depths of our stellar neighborhood. I hope this journey has helped you see the cosmos with new wonder, to feel its scale, its beauty, and its quiet power. The universe is vast beyond imagination, and the more we learn, the more mysteries unfold before us. If this exploration inspired you, continue to ask questions, to observe the sky, and to seek knowledge. Space has no boundaries, and neither does human curiosity. Our journey may end here for today, but ahead of us lie countless new discoveries waiting to be revealed among the stars.